Okay, so the purpose of today's note is to be able to look at motion on a position time graph. So we're plotting an object's position over a period of time. And we want to be able to talk about the type of motion. And in order to do that, we need to understand what the word slope means. So I'm just going to take a few minutes to review. Hopefully this is familiar to you from math class in previous years, but how to calculate slope and what does it actually mean. So I've got a graph here of somebody's position, an object's position, over time. And I've just sketched it in. It's not really that important that we have a perfect scale here, but I just want to review with you how to calculate slope and what that looks like. Okay, so we have somebody's position is changing. Each second we are moving so many meters east away from some point. So the first thing I just want you to know about position time graphs. This x-axis is what we call a reference point. A reference point is just a random point that we choose that we can talk in relation to. So if we know that we have a vector quantity and it has a direction, we can say that it's moving east in relation to some point. That is our reference point. And on a position time graph, it's always this horizontal axis. Okay, so back to the slope calculation. We have a straight line that's at an angle. Okay, and what we want to comment on is the slope. The slope is how steep is that angle. Well, we know that no matter where on this line we take or calculate the slope, it's going to be the same. So it does not matter what 2 points you pick on a slope calculation. So I picked nice easy numbers to work with. So the point plotted at 1 and 1, and let's say another point plotted at 3 and 3. It doesn't matter where on this straight line we calculate slope because the slope of it is the same if it's a straight line, no matter where you are. You pick your 2 points. Now we connect them into a triangle. So we go over, which is our horizontal change in distance, and then our vertical change in position, okay, on our graph. So if you recall from math class, slope, we use the variable m. And that represents your rise over your run. And from our actual graph, that represents the change in the y values or vertical distance over the change in the x values or horizontal distance. And what that also, if we recall from one of our earlier notes, this is the same as that delta symbol, which means final minus initial. So if we work with the 2 points I chose, our vertical change is 3 all the way down to 1 if we use our vertical axis, and our horizontal change is 3 all the way over to 1. Okay, so this is a change in 1, 2. So our change in x is 2, and our change in y is also 2. And so if we plug that in, we end up with 2 over 2, and that equals 1. And so it's saying our slope is 1, which means for every 1 unit we move horizontally, we also move 1 unit vertically. 1 horizontally, 1 vertically. And if it were steeper, then this number would be larger, and if it was less steep, this number would be smaller. And now the reason I wanted to go through this example is when we take the slope of any graph, it's always the change in your y-axis over the change in your x-axis. This also helps us figure out what units we're going to put in our final answer. If we know that the change in our vertical axis is meters and the change in our horizontal axis is seconds, we're actually taking meters divided by seconds. So our final units for this is 1 meters per second. And that also tells us that when we take the slope of a position time graph, we're actually calculating the velocity. That's what we're actually doing when we do that. So now what I want to do is just look at the different types of graphs, the different shapes that we can get and what they mean. Just do one at a time here. So what I'm going to do is give you, they're always going to be position over time, and this is going to be our positive direction in the east direction. So remember, I think I told you in a previous note that you should be familiar with your directions, north, east, south, and west. And then if we think about them like a graph, East and north are generally our positive values. West and south are generally our negative values. So if we want to talk about this graph, we have a horizontal line. Over time, that horizontal line is not changing. So all we can say, first, our slope is 0. There's no slope. There's no rise over a run. Okay, we have 0 rise. It's horizontal. Slope is 0. What that means is that the object is at rest. So when you have a horizontal line on a position time graph, your object is at rest. What else can we say about it, though? It is above the x-axis, so we can say that it is east of some reference point. If we actually had numbers on this graph, we could actually say how many meters east it was of some reference point. But remember, this horizontal line here, this x-axis, is our reference point. We relate all of our directions in relation to this. So some of you might actually be guessing now, what happens if we were to go below the x-axis in the negative y direction? Well, we're on the other side of a reference point, so that must mean that anything below the x-axis is in the west direction. Okay, so when we're talking about the whole first part of this unit, we're talking about one-dimensional motion, which means if we're moving east as a positive, the opposite of that is west. We don't combine different dimensions of motion until the second half of this unit. So you can assume everything that we're talking about is happening in a straight line. So a picture to go along with it, we have a person's going to be our reference point, and the object that we're talking about on this graph is going to be a ball. And so what's happening on this graph, an object is at rest east of some reference point. Next one. Now we have a horizontal line still, so we know the slope is 0, and then we know the object is at rest. It's not moving, it's not changing its position over time. But it's in the negative y values, and this y value here represents our position. And remember, our positive is east, our negative is west. So we can comment and say that the object is west of some reference point, so we've got the ball on the other side of the man this time. Okay, and now we've got a line with a slope, right? There's some steepness to it. As we move to the right, it's increasing. It's above the x-axis, so we can say it's east of a reference point. And if we can calculate the slope of a line, no matter what its steepness is, we can say that it has a velocity. And that straight line tells us, remember, no matter where you are on that line, your slope is always going to be the same. That also means that it's moving at a constant velocity because its slope is not changing on a straight line that's at an angle. Okay, and as time passes, we're moving further and further away from our reference point in the east direction. So we can say that it's moving east at a constant velocity. Okay, and so this could be somebody moving east at a constant speed or velocity. And now the only difference from this graph to the next one is we have a steeper line, which means a steeper slope. Only thing that changes here is that we can say that it's moving faster in relation to the one we just talked about. So maybe it's a car moving at a constant speed. Constant speed still because we have a straight line. And remember that when we take the slope of any straight line on a position time graph, we're actually calculating velocity. And no matter where you are on that straight line, it's not changing. So that tells us that we have a constant velocity. Okay, and so now here we've got another one. Remember, this horizontal line is our reference point. Any positions above is in the east direction, positions below is in the west direction. So we start east of some reference point. We decrease from left to right. That we call a negative slope. Okay, if you were to calculate that, you're going to end up with a slope in meters per second again, but it's going to be a negative slope. You'll have a negative answer. And all that tells us is that it's moving west. It's still a straight line, so it still has constant velocity, but as time passes, we're getting closer and closer to the reference point. And because we started east of it, it must mean we're moving in the west direction. Okay, so fairly steep line, a car moving in the west direction. And I think that might be it for this page. Okay, so now I just wanted to go through a couple of examples if you had to talk about a graph, what might be happening, because these tend to be tricky for some people. So remember, always on a position time graph, our horizontal axis is our reference point, which means we're starting west of some reference point, because remember, a negative value of position means you're west of it. And we are moving at a constant velocity because we have a straight line, and we're getting closer to our reference point. And if we started out west of our reference point and we're moving closer to it, it must mean we're moving in the east direction. We reach our reference point, but we continue at the exact same speed right past it in the east direction, and we end up in a final position that is east of our reference point. That's pretty much all we can say about that graph. Okay, next graph. Segment A, we are moving east at a constant velocity away from our reference point. Segment B, remember, any horizontal line on a position time graph means we're not moving at all. We haven't changed our position from here to here, which means we're at rest. And then during segment C, we turn around, move west back towards basically where we started, we can say, at a constant velocity. Okay, and then the final one, in segment A, horizontal line means we're at rest, we're not moving, and we're on the reference point. And for segment B, we move at a constant velocity in the west direction away from our reference point, and then we stop again during segment C. Then we move back toward our reference point at a constant velocity and move right past it at that same velocity. And we end up in a final position that is east of our reference point.